What's good, everybody? Welcome back to another episode of Stonks Maxxing, so day 43. What I want to do is, I have some code pulled up here, just getting the pipeline set up, but basically, I always have to write down the current stock price, the forward PE ratio, and also the current stock price for the Sembit fund holdings that we currently have, that my school's endowment currently has. And so in order to make this a little bit easier, I think what I want to do is be able to somehow pull this pricing data directly from some type of API service. And I think I found one here. Price, this gives me the price. I wonder if this gives me the company share float. Float share is interesting. So it tells you there. Okay. Company share float, historical share float, all shares float. Does this give me the price on specific dates? Oh, quote maybe? Stock price change. Alright, yeah, let's take a look here. So simple quote. Right, okay. Let's see. So endpoints, we want. Okay, so I think we could say here API v3 base URL right. So we'll just do this. Base URL slash search nope quote short see invalid API key. Maybe we do this. Okay. So I wonder if there's a way we could get the dates. So API financial modeling prep API dates. API query date. Okay, let's think about maybe the forward PEs real quick then. Okay. So EPS, let's see here. Transcripts and news, FX prices. Analyst estimates. Call this query URL. Analyst estimates. And then do company ticker is equal to Apple AAPL. Okay. Oops. Query URL, then company ticker. Oh, shoot. Okay. Yeah, so I guess, damn. I don't know what the asterisk there means. Shoot. Earnings, maybe? Oh, okay, from, let's see this then. So basic URL, right? And then we want to change the earning calendar. Yeah, let's just see what happens if we do this. Oh my god. Okay, I guess we can't. You could just get the price, I guess. Quote. Yeah, I guess there isn't a way to get the dates. Is this forward EPS, forward PE? So is this percentage change? It's change over given. Okay, let's take a look then. Because maybe we could do this. So stock price change. I think this is probably, take a look. So Apple stock. 7.5%. Oh. Yeah, definitely more. Okay. Oh, okay, so let's say quote short. Okay. Okay, yeah, I think that probably makes sense. 12.49, which is a little bit less than. Oh no, it is 12.44. Maybe it's a few basis points off. So res 1, res 2. res2.json. Because the reason I'm kind of confused, the stock price matches up here with Google, but in terms of the 5-day percent change, it seems like this is 7.74%, while this is 7.61%. So maybe there is a slight difference there. This is a bit higher than what this is saying. I guess it shouldn't matter too much. I don't know. Yeah, I'm just gonna not worry about that too much then. So I think what I could do is probably do this. So for Micron, let's see if they have XLK. So there is, all right, def get price company tickers. Okay, so company tickers is equal to, do a list. So AAPL. I think Micron is also one of them. So Micron ticker MU. It's 0.10. Okay. It's very close, not super close though, but it's okay. So XLK and Cisco ticker CSCO. Okay. So for ticker in company tickers. Alright, so we'll do company ticker is equal to ticker, and then we'll do so base URL. Yeah. Okay, now we'll get the response. And then I guess we could get a dict too, right? So ticker price dict is equal to, and then we'll do ticker price dict. Actually, we'll do, oh yeah, so ticker price dict ticker, and set this equal to res.json, and we'll get the price, and then we will return the ticker price dict. Okay, and then let's do get price company tickers. Oh. Okay, maybe I'm confused then, right? Oh, okay. I think we do have to index this by 0 then. All right, nice. So we have the prices, and yeah, maybe we could get the weekly change too. So let's see, how should we do this? Should I do it separately? So okay, maybe I could do this, right? I'll get two things. So I'll create two functions. Def gets 5-day change, price change, and then we'll do company tickers. Price ticked, right? And then I think what we could do is we'll get the stock price change. Case. And we want the 5-day, so 5D, and then we will return the 5D price ticked. So we have get price, and let's also get price 5D, company tickers. All right. %. Yeah, I'm not entirely sure who. Okay, maybe if it's wrong by a little bit, I'll be fine. Okay, and so we have right, what if we did, so what if we zip these two? Price dict, price change dict. Right, so the zip object yields n length tuples where z is the number of intervals passed. Yeah, I don't think this is gonna work then. List, let's see. Oh, right, yeah, no. So this will zip the keys. Okay, let me try to think here. Maybe we want to combine this into one function then? So yeah, maybe we could get price 5D. Yeah, I wonder if I'll just do this then. So base URL, this is the same, right? And then we will do price query URL and then 5D price change query URL. Okay. Price response to this. Is equal to empty list, right? So this is the price change response. So we want the price change query URL, right? And then we want to add the price change response here, 5 days. So I think this one is just called price. Let's take a look. Oops. Right, okay. Let's maybe pd.dataframe, import pandas as pd. Oop. Frame. Okay. Transpose. Oop. So this is the price. Okay. I think that's how I'll do it. Okay. So transpose and df.columns is equal to, call this price, and 5-day change. Let's display df. Okay. So 5-day price is equal to df price times, so 1 plus right. So let me think about this. So price today is equal to 1 plus the 5D change times 5-day price, right? Or if you think about it, 5D change should be price today minus price yesterday, so 5 days ago. Let me divide this by the beginning price, divided by beginning price, so divided by price 5D go. Or we can think about this as so price today divided by 5D price minus 1. Okay. So what we could do then is, so if we add 1, we'll have 5D change plus 1 is equal to price today divided by 5D price. So if we want to get the 5D price, so we can multiply this over. So we do 5D plus 1 times 5D price is equal to price today. And then we could also divide this. So we have 5D price is equal to price today divided by 5day plus 1. Got it. So we're kind of discounting by the price in order to get. Okay, that makes sense. All right, so then we want to do divided by, so 1 plus df, so 5-day change divided by 100. Okay. Maybe we'll round this. Okay, so I think that's pretty good. I think if we just do a sanity check, so sanity check, should we divide this actually by 100 first? Yeah, I'm gonna just do this. And then 5D change is equal to 5D change percent divided by 100. Okay. Equal to df, call this 5D price times 1 plus df 5D change. Yeah, it's close enough. Okay, 41.3. Okay, yeah, I'm gonna delete this then. Okay, and then let's kind of grab all the columns that we really care about. So df to price and then 5-day price. Okay, that's pretty good. Don't need these anymore. Don't need this. Okay, so let's just increase the tickers then. So let's, I believe we don't need this either. Okay. Yeah, maybe it'll be helpful if I do this. Okay, and then, so let's take a look at what other companies I have here. All right, Intel. It's the Intel INTC. So Datadog, DDog. Yeah, I might pull this over here. So Duolingo, stock, so DUOL, Qualcomm, QCOM, Quality Communications. Okay. I think TSMC is TSM, I remember that. And then Snowflake, I think it's just Snow. Make sure that was Snowflake. Okay, and then Tenable, 10B. Yeah, okay, this is very nice. I can just copy this instead of having to manually get it. Now, should I just cheat and make the PE kind of the trailing PE? Nah, I feel like with tech, it'll be tough because, yeah, it'll be tough. It'll be tough. All right. I think a lot of these companies are considered growth, so when you have trailing PE versus forward PE, which is using, I believe, the expected forward earning per share, so the expected earnings per share in the future, and then probably going to have a huge difference because some of these companies just aren't profitable. All right, well, I think this is very nice. This is a nice tool that we've made. We did hard code this, but that's okay. So yeah, let's see. I'm gonna go brush my teeth real quick, but I still have a bit of stuff I need to do in terms of the computer stuff. So the company specific stuff, and then also the sector news. I'm gonna come back though for this. Yeah. Okay. I'm back. Alright, so let's take a look at the sector news. There's one thing I wanted to note about. I wonder if oh, right here. You know, this is interesting because I thought high bandwidth memory does. I thought it includes or utilizes the double data rate 5, right? So DDR, I think, is double data rate. Synchronous SDRAM. Okay, so I think what I might do actually is high bandwidth memory. I think Asianometry has a good video about this 6 years ago. Wow. Okay, so this is before all the tech hype, the AI hype. Yeah, I'm gonna watch this real quick, and then there's also something here. Okay, yeah, this could be interesting too, but I'll do this first.
HBM does not refer to a special type of dynamic RAM memory cell or a special chip. Rather, it work by Dylan as usual. In it, Dylan
Semi-analysis, let me see. Subscribe. This could be interesting. So what is Substack? I guess it's a blog. Okay. Damn. Okay, that's unfortunate. To pay for some of these $500 though, there's no way I can afford that.
Strange post on semi-analysis. Good work by Dylan as usual. In it, Dylan and the team profile NVIDIA's H100 AI Super Accelerator, a monster of a GPU that costs something like $20,000 and is not for gaming. This GPU uses an interesting new type of memory, high bandwidth memory. This GPU costs something NVIDIA's H100
HBM maybe take some notes. So, Asian geometry, special memory powering the AI revolution. So, what is it? Semi-analysis. This is Substack. Dylan Patel. Who is that actually? I'm gonna quickly take a look real quick. Okay, I might take a look over here. Okay.
AI super accelerator, a monster of a GPU that costs something like $20,000 and is not.
So NVIDIA H100 costs $20,000 GPU.
Gaming. This GPU uses an interesting new type of memory, high bandwidth memory or HBM, from the Korean memory maker SK Hynix.
Okay, so this uses HBM from SK Hynix. The HBM3 variant.
Namely the HBM3 variant, the first commercial product to have it. Dylan also mentions that AMD's own forthcoming AI accelerator, the MI300.
The MI300 also uses HBM. So AMD's MI300 is an AI accelerator. So I guess this is a semiconductor built for AI training and inferencing.
It also uses HBM. Ever heard of this type of memory before? What is it, and what makes it the preferred choice for these AI chips? In this video, a deep dive into the special memory powering the deep learning revolution. But first, let me talk about the Asian Geometry Patreon. Early access members get to see new videos first, as well as selected references for those videos. Early special chip, rather to a special type of dynamic RAM memories. HBM does not refer to a special type of dynamic RAM memory cell or special chip. Rather, it is a standard administered by the Joint Electron Device Engineering Council.
Okay, so HBM is not, so I got this wrong, is not a special form of DRAM, but it is a standard built set by the JEDEC, Joint Electron Device Engineering Council, right? I think that's what it is, JEDEC. It's in Arlington, okay. What does JEDEC stand for?
Council, or JEDEC, for interfacing the DRAM and the compute.
Oh my god, scared me.
HBM introduces the concept of stacking the DRAM dies and running many independent memory channels through the stack. The goal is to provide very high data rate transfers for more advanced computing applications, like to provide running many independent memory channels through the stack. The goal is
Okay, interesting.
HBM introduces the concept of stacking the DRAM dies and running many independent memory channels through the stack. The
I'm not too
goal is
sure
to
what a
provide
DRAM die is. Let's see. So HBM introduces the concept of stacking the DRAM dies and running many independent memory. So I guess this is a die. So what is DRAM die? So overclocking, if I remember, is pushing a CPU or any type of chip beyond the stated capabilities. Okay. So it seems like dies refer to the specific RAM chip on a RAM stick. Okay. Maybe I'm gonna trust this guy on Reddit, but let's take a look at what RAM die looks like on Google Images. So I guess this itself, these black squares on, I guess you could call this a stick of RAM, is the RAM die itself. This picture, the big green thing is the RAM stick, and the small black chips are the RAM dies. So stacking the DRAM dies, running many independent memory
channels through the stack.
Channels through the stack. Yeah, so I guess maybe this is you're stacking the chips together. So you're stacking the black chips together, and I don't know what the independent memory channels.
Stack. The goal is to provide very high data rate transfers for more advanced computing applications.
Okay, so yeah, the goal is to provide very high data rate transfers for
more advanced computing applications, like those for AI, which are more amenable to parallelism. The vendor can also choose to add a logic base die, as is shown in the JDEC spec diagram.
Same micron. I think they have. Okay, yeah, I think that's exactly what this is. It's just you're stacking a shit ton of those chips on top
This
of
additional
each other.
logic is for redistributing signals, test logic, and other external communications. JEDEC standard defines for the manufacturer how the HBM system has to work and what features they need to support. It helps with the commands and signals sent through the memory channels in the DRAM stack, for instance. But it does not specify how the vendor might structure the stack, nor does it specify things outside the stack. This allows various HBM vendors in the memory industry to offer a differentiated product. HBM buyers can put your HBM stack right on top of your CPU or GPU die, or do what AMD/NVIDIA did, which is to add a silicon interposer to connect multiple HBM die stacks to your GPU.
So maybe this is kind of the packaging step of how you can structure your semiconductor. Damn, yeah. Sample of
HBM buyers can put your HBM stack right on top of your CPU or GPU die, or do what AMD/NVIDIA did, which is to add a silicon interposer to connect multiple HBM die stacks to your GPU, like a PCB.
I don't know what a PCB is. So, example of, what do you call this? Packaged semiconductor that combines so that connects a CPU/GPU system on a chip die with the HBM DRAM memory stack via a silicon interposer. So I don't know what a silicon interposer is. Let's take a look. Okay.
洗过了。
Okay, thank you. So interposer. Let's say means to put between and are used in what is a PGA package? Used in semiconductor manufacturing. Semiconductors to connect multiple dies. To connect dies to each other. Remember, this example, the memory is connected to the CPU via the interposer. I think that's kind of the most high level I can get. Okay.
JDAC also administers other standards like DDR, LPDDR, and GDDR.
So, okay, JDEC also administers other standards like DDR, so double data rate. Not too sure what LPDDR means. GDDR.
DDR is the standard you might be most familiar with, used for general purpose memory modules like those you put into your PC.
Okay, so this is a DDR stick of RAM.
GDDR. DDR is the standard you might be most familiar with, used for general purpose memory modules like those you put into your PC. The traditional memory interface standard for graphics cards is GDDR, or Graphics Double Data.
Okay, right, I think we had talked about this last time actually. So the graphics double GDDR is the graphics double data rate standard.
Rate. Right now, they are on their 6th generation, GDDR6, and there are a few gaming cards using it. So why do we need another standard? There are a few things about GDDR that make it less suitable for heavy AI processing.
GPUs.
First, while each new GDDR standard does feature higher data rates, they also employ a point-to-point connection. This means that each...
Okay, so what is a data rate? I guess it's fair to say, right? So data rate refers to the... Okay, so I guess that's what they say, I mean, megabytes per second, right? So that's how much you can transfer a single byte, or maybe megabyte. So I think mega is maybe 100 bytes. Kilobyte is 1,000. Megabytes probably 1,000,000. Yeah. Gigabyte is 1 billion. And then terabyte is 1 trillion. Okay, that makes sense. This is actually interesting. So I remember bandwidth, without looking at it, is how much data you can store or maybe transfer in a single signal. Bandwidth is width expression. Data rates. Geeks for geeks. Oh, okay, so this is interesting. So bandwidth is 100 Mbps, so megabits per second. But the data rates is 50 Mbps. It means the maximum of 100 MB, so that's 1,000,000 bits, not bytes, and 100 million bits of data can be transferred, but the channel is transmitting only 50 MB of data per second. So how do you increase that transfer so you can meet your bandwidth threshold? It'll decrease your bandwidth. Okay. So remember that data is, so data itself is represented as a bits or a byte sequence of 8 bits. So bit rate, the number of bits that are conveyed or processed per unit of time. Similar to the idea of a bit rate. So I guess at a high level then, data rate just refers to the speed at which data is transferred over some type of network, and or maybe a channel. So channel is just a way of connecting different, I guess in this case, dies or chips. But when you think about it, maybe at kind of, as you go down the level of the pyramid of complexity, the next level maybe say that, all right, the data that's represented is really the bits or the bytes, and it's how fast you can send bits over a network through, when you measure it across time maybe. So data rates is usually measured in bits/bytes per second. Okay.
Memory channel. They also employ a point-to-point connection. DDR standard does feature higher data rates. They also employ a point-to-point connection.
So I think what that means is that, okay, every new generation of standards, you're able to transfer data faster than previously. Okay, so that's just what he means by double data rate. Now, with every new generation of graphics, DDR double data rate, the data rates increases. GDDR also has a point-to-point connection. Okay.
This means that each memory channel connects to just one module of memory.
So this means that each memory channel connects to just one module of memory. I don't know exactly what that means. Each memory channel.
This is in contrast to HBM, where channels run through all the modules in the stack. GDDR's single channel makes it harder to scale the system's total memory capacity, GDDR to HBM, where it's just one module of memory.
Okay, so there's two things, right? So a memory channel and a memory module. What is a memory channel versus memory module? So memory channel refers to the connection between the CPU/GPU to RAM. Okay, so the capacity here is 8 gigabytes per second bandwidth. Huh. Quora. I think his example is pretty good, right? Oh, never mind. Let's see, Quora. Let me see if the Reddit also has anything. Okay, so double data rate just means that you have two. So I guess you're doubling the amount of data that can be transferred. Hey, Professor Bruce Jacob. Okay, I could have Maryland. I didn't realize. I guess he's the GOAT. Oh my god, that's so expensive. Maybe I can borrow it from my school's library though. Okay, I guess this one doesn't really work anymore. Okay. But do you want to add his name here? Because that seems interesting. And I wonder if other notes. So, Professor Bruce Jacob, U of Maryland. Yeah, let me see. So, Testudo, schedule of classes. Jacob. Bruce. No. Has he taught recently though? Spring 2024. Maybe Planet Terp. Bruce Jacob. Alright, so it seems like ENS. ENES. It's exascale. Floating point operations per second. This is probably taking a break right now. No. Okay, he left, seems like then. Okay, shoot. That's unfortunate. Okay, oh well. Okay. Has really good book on DRAM.
This is in contrast to HBM, where channels run through all the modules in the stack. GDDR's single channel makes it harder to scale the system's total memory capacity because it means we have to scale that single module's memory capacity, which essentially requires us to shrink down the DRAM cells even more, which is hard. I did a whole video about this a while ago discussing the 3D DRAM cell. Future shrinks seem to require new capacitor structures like the pillar, which may or may not be actually manufacturable. By vertically stacking the modules, HBM makes it conceptually easy to raise the memory capacity. There are also some physical size gains as well when it comes to horizontal floor space being taken up by more memory. More capacity is good because it means we don't have to go to the secondary memory systems, hard drives, etc., for more data as often. In April 2023, SK for more it means being taken up by more memory structures, DRAM, which DDR's single channel makes it harder to scale the system's total memory. This is in contrast to HBM, where channels run through all the modules in the stack. GDDR's single channel makes it harder to scale the system's total memory capacity because it means we have to scale that single module's memory capacity, which essentially requires HBM, where channels run through all the modules in. This means that each memory channel connects to just one module of memory. This is in contrast to HBM, where channels run through all the modules in the stack. GDDR's single channel makes it harder to scale the system's total memory capacity because it means we have to scale that single module's memory capacity, which essentially requires us to shrink down the DRAM cells even more, which is hard. I did a whole video about this a while ago discussing the 3D DRAM cell. Future shrinks seem to require new capacitor structures like the pillar, which may or may not be actually manufacturable. By vertically stacking the modules, HBM makes it conceptually easy to raise the memory capacity. There are also some physical size gains as well when it comes to horizontal floor space being taken up by more memory. More capacity is good because it means we don't have to go to the secondary memory systems, hard drives, etc., for more data as often. In April 2023, SK Hynix unveiled their latest HBM3 chip with 12 layers and 24 gigabytes of memory.
SSD.
This is an expansion from the 8 layers you had on prior HBM3 configurations. Second has to do with how we do memory.
Yeah. Marciano. Yeah, I'm not him.
Wait, the guy in there?
Yeah. He cheated on me, so I moved out and then.
Bandwidth. Bandwidth refers to the rate at which data can be read from and stored in the memory.
Refers to the rate at which data can be read and stored from a memory. So bandwidth refers to the rate at which data can be read from and stored in memory. So how is this different than data can be read and stored from memory? How's this different from data rate? Genometry?
It has a few major components in it. The clock
Right, okay. So, clock frequency,
the number of data transfers within each clock cycle, and the width, the clock frequency, the number of...
so this is the number of data transfers within each clock cycle. So if I remember correctly, each GPU or CPU, each logic chip has its own internal clock, and a cycle just refers to that. Each tick of a clock, so maybe it's a second. I don't know if it's measured in seconds. What is a clock cycle then? Clock cycle basic unit of time in a CPU. It represents one complete operation of the CPU, including fetching, decoding, executing, and storing data. So during each clock cycle, the CPU performs a series of tasks to execute instructions, process data. So Lenovo. Okay, so that is important. The number of data transfers within each clock cycle. And a clock cycle is really just a basic unit of time in a CPU. So it represents one complete operation of the CPU, including fetching, decoding, executing, storing data. During each clock cycle, so the CPU performs a series of tasks to execute instructions and process data. Okay, so I guess I got that wrong, right? The clock cycle really is this basic unit of time. It represents, so in this case, one operation of doing a bunch of different tasks from fetching, decoding, executing, and storing data. So fetching, decoding, executing, that probably refers to fetching data, decoding it, executing some type of instruction, and then storing whatever is the result of executing that instruction back into data, back into memory, or maybe storage. Right, process the data, right. Okay.
Data transfers within each clock cycle.
Width of the memory bus.
And the width of the memory bus. So if we want to get a higher rate, then there are a few levers that you can pull to go about it. You can raise the clock frequency or the width of the memory bus.
So you want to get a higher rate of what? Oh, okay. to increase the bandwidth, the rates at which data can be read, stored. There are a few levers you can pull. Increase the clock frequency or increase the memory
Pull
bus
to
width.
go about it. You can raise the clock frequency or the width of the memory bus. GDDR features a relatively narrow memory bus, which limits how much data we can send through at any one time. So GDDR gets a higher bandwidth by ramping up the clock speed. So think of it as
Some features are optional, therefore.
kind of like a thin but very fast moving stream. GDDR6's narrow and fast approach is great for tasks that require a lot of sequential calculations. Streaming data, complex physics for tasks that require stream. GDDR6's narrow and fast approach is great for tasks that require a lot of sequential calculations. Streaming data, complex physics calculations, rendering frames. But here's the downside. Higher clock speeds are a formidable engineering challenge and consume more power.
Okay, so higher clock speeds are a really hard engineering challenge. Consumes more power.
This is in part due to having to distribute clock signals throughout the chip, and also that the transistors in the memory chips and the memory bus have to switch more frequently. And with high
So transistors need to switch more frequently on memory chips and buses.
higher power consumption, there is also more heat. And of course, electricity is not free. At some point, you're bumped.
Electricity is not free. So what does this mean? I guess if there's too much energy, it just blows up. I don't know.
Bumping your head against the system's overall power budgets. So the approach that HBM takes is referred to as wide and slow. We widen the memory bus, 1024 bits per HBM3 stack, compared to DDR5's 64.
Oh, interesting. HBMs don't actually lower the clock speed compared to GDDR, so graphics double data rates, but will increase the memory bus width.
4 bits, while operating at a lower clock speed. This makes it a slow-moving but very wide at a lower compared to DDR5's 64 bits, while operating at a lower clock speed. This makes it a slow-moving but very wide river. The result is that we are able to transfer more data while consuming less energy on a per-bit basis.
Actually, I like this. So, geometry describes this as a wider, slow-moving river that can transfer a lot more data at a single time. So this means you increase the bandwidth.
I dug up a 2013 slide from the AMD announcement claiming a 40% decrease in memory power consumption while boosting system performance by 65%. NVIDIA is making billions selling AI accelerators, so it's interesting that the HBM standard that built a 40% decrease in memory power consumption while boosting system performance by 65%.
AMD slides. HBM power efficiency.
Power consumption while boosting system performance by 65%. NVIDIA is making billions selling AI accelerators, so
Not
it's
too sure
interesting that the HBM standard that their accelerators use
system performance means.
comes from AMD. AMD started that their accelerators use comes from AMD. AMD started on what would eventually become HBM in the 2007-2008 time period as they were working through the broader technical issues around die stacking.
Huh. So AMD was the original pioneer of HBM in 2007, 2008.
Time period as they were working through the broader technical issues around die stacking.
Okay.
In a 2015 interview, Brian Black, senior fellow at AMD and said to be the godfather of the chiplet,
So Brian, oh, hey, that's me. So Brian Black. Working on this AMD at the time. He is the godfather chiplet.
explained that his
This guy.
team started architecting HBM
Oh,
after
nice.
seeing the limits of
Didn't see
GDDR, back then GDDR5 rather than GDDR6. The limits of it explained that his team started architecting HBM after seeing the limits of GDDR, back then GDDR5 rather than GDDR6, especially when it came to power consumption. So in 2011, AMD announced that they were partnering with SK Hynix to develop something to essentially replace the GDDR standard, particularly with regards to this power consumption issue. Especially of G explained that his team started architecting HBM after seeing the limits of GDDR, back then GDDR5 rather than GDDR6, especially when it came to power consumption. So in 2011, AMD announced that they were partnering with SK Hynix to develop something to essentially replace the GDDR that they were partnering.
Okay. In 2011, AMD partnered with SK Hynix.
Partnering with SK Hynix to develop
something to replace the GDDR standard. So what were they having problems with again? To its limits.
rather than HBM after seeing the limits of GDDR, back then GDDR5.
So I guess we had talked about the single memory. So single memory channel difficult scaling problem. lots of power consumption.
rather than GDDR6, especially when it came to power consumption. So in 2011, AMD announced that they were partnering with SK Hynix to develop something to essentially replace the GDDR standard, particularly with regards to this power consumption issue.
That's crazy. I was just on Lenovo's website, now I'm getting an ad for that.
Key to making HBM work are these channels running through the DRAM die stacks. These are made up of what we call through-silicon vias, or TSVs.
TSVs, micro bumps, were a key innovation. TSVs through silicon vias. So who is this guy, Asianometry? He's only 26 years old. Wow. How old is John Y? Okay. Yeah. No, that's cool. So they have a lot of deep dives. So I think what I'm going to do now, I took a lot of notes on some of the technical stuff, but I have kind of got distracted here. And I still need to kind of go back to week 5 here of Senbits and maybe talk a little bit about the sector news. So now that we kind of understand a little bit more about the technical aspects of this, so HBM is a standard that seems like it combines DRAM chips together though. Let's see, so are DRAM chips used for stacks? So yeah, it seems to be some competing things. So let's take a look at Micron high bandwidth mem. Yeah, greater than 1 terabytes per second. Jesus Christ.
Introducing new Advil Targeted Relief, the only topical pain reliever with 4 powerful pain-fighting.
Delete this. Gigabits per second. I don't know what per place it means, right? Okay. Yeah, so I think that was kind of misleading. It's okay. I might dive a little bit deeper into the technical behind that. I think starting off with DRAM though is probably the best way to go. But let's go to AI news because that's what I usually like to start with. Maybe semiconductor news. Let's see, semiconductor news. What's this? Okay. I guess this is interesting and from a technical standpoint. ML perf benchmark. Euro max, i.e. Oh, four E's. Okay. 3 E's. I'm surprised Google Docs knew about that. Commentary. Let me see something real quick, actually. Oh. Wait a minute. Okay. So let's see. ML perf, let's take a look what that is. Is a performance benchmark. Is a series of benchmark to compare the ability used in pair systems. So I guess systems, so usually composed of hardware, software. Basically just hardware components like GPUs, ability, a variety of tasks from training to inference. Okay, so this is interesting. Further okay. Oop. Comparing companies that make AI accelerators. Google, Intel, AMD, NVIDIA's Hopper architecture dominated the results on the new LLM fine-tuning and graph neural network benchmarks. That's kind of crazy. Systems refer to giant computers or collection of hardware components. Referencing AI models. So I guess accelerators are another word for GPUs. Seems like it, or maybe, so GPUs, they're maybe used for things like gaming as well. So they're a specific type of GPUs that are built specifically for AI training and inference. Interesting. Okay. Further cementing their lead in their technical lead in the AI accelerator. So the GPUs optimized for AI training and okay. Yeah, so this, I'm going to be honest, I don't fully understand. I'm going to put this here for now, and I think maybe it'll be worth going into a little bit deeper. So this is, I'll say AI plus semiconductors. Combine this into one. Software news. The impact engineering. Morning Brew, Computer World. Wait, so maybe I could just combine that into one here. So I might do that actually. I might combine that into one, and I wonder if there's anything I want to add for software. Probably not. Cisco. Let's see if there's anything for Cisco. Okay, so actually this could be interesting. So Cisco. Accessing shell to board was pointed to the board of directors. Let's go. Right. Oh wow. Okay, so she's part of the Federal Reserve Bank. Commentary. Shell is okay, so she's on a few. Okay. Interesting. Master of Science in Electrical Engineering, Computer Science from the University of California, Berkeley. I see Ekta Singh Shell. Serves on the boards of few publicly traded tech companies and is being brought in for her experience in data security and services. So what does ChargePoint do? Okay. red, white, and So, yeah, what did I think? So I remember, I think last week I talked about Cisco's security offerings, maybe something like that. Security products. Okay. Non-current. Okay. Subscriptions. Yeah, this is a really low margin business. Jesus Christ. I'm looking at the ChargePoint Holdings thing. Okay, so I think with this, I probably am going to stop the stream here. I might want to move some of the stuff from the notes into... Yeah, probably going to want to move some of this stuff from notes into my flashcards, but I might do that in another stream. I'm kind of tired right now. Might need to go get some water, go for a walk, but yeah, I don't want to be looking at my screen for super long. Oh, yeah. Alright, yeah, so trying to think, do I want to stream later and kind of go over maybe some things to talk about or maybe to study this year or this summer? Okay, I think I might. I think it's worth spending some time today. Alright then, with that, we'll catch you guys the next one. Thanks for tuning in. Peace.